let's say we have a person sort of hanging. It's just sort of hanging out. Let's say this person weighs 150 pounds. 150 pounds. There we go. And he's not just hanging, he's actually hanging from a rope. So he's hanging for his life. So what's keeping him from falling? After all, he's got a force of gravity, so we'll call that F of G, equal to 150 pounds. So what's keeping him from falling? What's fighting that force? Well, that's the rope itself. It's the force of tension pulling up. And if he's not falling, then the force of tension also has to equal 150 pounds. So what we'd say is the sum of all forces equals, well, it equals the force of gravity. Force of gravity plus the force of tension, which clearly equals 0. And when the sum of all forces equals 0, we call this static equilibrium. And that looks so much nicer. All right, so let's draw another scenario to kind of clarify some things about static equilibrium and reactionary forces like force of tension. So let's say the same person is hanging. The same person is hanging onto this rope. But this time he's grabbing onto some suitcase. So he's hanging on to this suitcase here. And the person still weighs 150 pounds. And let's say the suitcase weighs 200 pounds. So now we have a much bigger force of gravity. We've got an F of G equal to, well, 200 plus 150 is 350 pounds. But my question is, what happens to the force of tension? What happens to the reactionary force fighting this? And the answer is it increases. As the action force rises, so will the reactionary force. So the force of tension will become 350 pounds as well. So we still get the sum of all forces equals 0, which means we still have static equilibrium. Equilibrium. So now I want to present a third example to you. Let's say we have the exact same situation. The same guy's hanging off a rope. He's still hanging on. He's still hanging on to his briefcase. But let's say the briefcase this time is a little bit heavier. Let's say it's 202 pounds. And the person still obviously weighs 150 pounds. So now the force of gravity is 352 pounds. Now naturally, as the weight rises, so will the reaction force. As the initial force rises, so will the reaction force. But let's say hypothetically that this makes it too great. Let's say the rope can't sustain it, and it snaps. It snaps right here, because it's its weakest point. So the force of tension tried to rise. I'm trying to write snap, not static, snap. So the force of tension tried to rise to meet the new force, the extra weight, but it couldn't. So the force of gravity sort of overcame the force of tension. And now we've got this guy who's falling into, I don't know, a pit of sharks or something. Exclamation mark, exclamation mark, exclamation mark. Okay, there we go. So in this situation, the sum of all forces will not equal 0. So we are not in static equilibrium. Static equilibrium. So as you can kind of see, as the force of gravity goes up, the reactionary force, in this case the force of tension, will rise up to meet it until it reaches its breaking point. But the point I want to get across in this video is if the sum of all forces equals zero, then it's static equilibrium. And you can tell whether or not it's in static equilibrium, whether or not things are breaking, whether or not things are accelerating, if some force is unanswered. Now I want to be clear here. I want to make a point here. I want to make a note that just because something is moving doesn't mean it's in static equilibrium. Right? Or doesn't mean it's not in static equilibrium. So moving things, let me make this wider here. Moving things can be in static equilibrium. It has to be accelerating. So just because something's moving doesn't mean it's not in static equilibrium. And the reason is because the sum of all forces tells us if it's in static equilibrium, not the sum of all speeds. And you say, well, we're not talking about, you keep saying accelerating, not speed. Well, that's because force equals mass times acceleration. There we go. And force does not equal, and I'll put a little dash in a second, force does not equal mass times speed. So just because it's moving doesn't mean it's not in static equilibrium. And let me draw that a little bit better. For example, the world is always going around in a circle. It's always moving, and yet the bridges in our world are still in static equilibrium, even though they are constantly moving through space.